Good afternoon and good morning, depending on what part of the country you are. My name is Pedro Arduino, and I will be your moderator for this webinar. I am very sorry for the inconvenience that we just had with the audio. COGGE is the Committee on Geological and Geotechnical Engineering. It is one of the standing committee of the National Academies of Science, Engineering, and Medicine Board of Earth Science and Resources. This committee, COGGE, was established as the focal point within the National Academies for Government, Industry, and Academia on technical and public policy issues related to earth processes and materials, soil and rock mechanics, responsible human development, and mitigation of natural and human hazards. If you have any questions about this committee, COGGE, please contact Samantha Maxino from the National Academies staff group. She's the director of the committee. This webinar is part of a quarterly webinar series produced by COGGE through the support of the National Science Foundation. And the webinar is going to be posted on YouTube. An announcement will be sent once the file is available. Before we begin, I would like to acknowledge actually Samantha Maxino, Courtney Devine, and Mandy Enriquez for helping organize and produce this webinar. They are in charge of all the details. Dr. Craig Davis, also part of the committee, will assist with fielding questions from participants following the presentation. The audience can submit questions at any time using the Q&A tab that you have at Zoom. And Dr. Davis will try to pose as many questions as time permits. We will also have a survey, so please respond to the survey questions so that you can help us improve this webinar series. And also a small disclaimer: any opinions, conclusions, and recommendations expressed by Dr. Halpin or anyone during the webinar are those of the individuals and do not represent conclusions or recommendations of the National Academies of Science, Engineering, or Medicine. So with that, I would like to introduce you our presenter, Eric Halpin. So Eric is a registered professional engineer working as a dam and levee consultant specializing in risk and safety programs. He recently retired from the Corps of Engineers after almost 40 years of service, where he led the agency dam and levee safety programs, as well as the National Levee Safety Program. He has engineering degrees from Clemson University and Oklahoma State University. Currently, he is the principal of Halpin Consulting, LLC. With that brief introduction, I give the floor to Eric. We are very happy to have you here. Eric.
Thank you, Pedro, and thank you, National Academies, Sam and Marty, for the invitation to speak. You know, I worked just across the street from the headquarters of the National Academies for over a decade, and so I came to be familiar with what you do, the important work you do. So originally I was going to talk to you about how geoprofessionals should communicate with decision makers, and I've decided to replace communicate with influence. That's a great Washington, D.C. word. So influence gets a bad rap, but it's really what we're talking about. And in Washington, D.C., it's actually the main currency for how things get done. But it's really no different in this broader industry and profession that we're a part of. So I'm a geoprofessional myself, and I'm just going to come at this with my own experiences and opinions and what's worked and what hasn't for me on this topic. So here are the topics I'm going to talk about. And first, I'm going to, in order to talk about influence, I'm going to talk a little bit about ourselves and kind of, if we understand who we are, we can understand how we can be better influencers. A little bit on the basics of influence and decision making, particularly in the modern context. And then spend most of my time on influence and decision tactics that work well and those that don't work well. And then kind of wrap up with a little piece on looking forward and what are the trends, challenges, and opportunities for decision making and decision influence. So I've been a geoprofessional, decision maker, someone that influences decision makers, sometimes all at the same time. And most of my experiences really come from the core, where I managed a portfolio of over 3,000 infrastructures, where we invested over $1 billion a year. And I was really one of the key folks responsible for influencing decision makers in the administration and Congress, but more importantly, with the gatekeepers for the decision makers. So that's the congressional watchdogs like Government Accountability Office, and the administration watchdog like Office of Management and Budget, and some of the honest brokers like the Congressional Research Service. So I do the same thing now, only decision makers are and gatekeepers are people in the corporate world. So it turns out that they're not so different. So too often we kind of paint ourselves in a corner by describing a binary world where we say, just trust us, it's technical, and then that's our promise back to people, clients. In reality, we're managing risk, and it would be healthier to have conversations like this, where we recognized our own limitations in knowledge, outcomes, and influence. So along these lines, I'm going to be talking about risk quite a bit in the presentation. So the first part is really to look inward and try to understand where we're coming from. That's important to really kind of try to figure out how to be better influencers. We're not monolithic in our experience, our perspective, or our objectives regarding the geo-profession. So this was evident in the dichotomy between the ASCE Scorecard results, which gave all sectors bad grades, and the president's $2 trillion infrastructure plan. Dams and levees were virtually left out of that $2 trillion plan, primarily because we lacked the sophisticated influence that other sectors like transportation, commerce, and technology exerted on those decision makers. So all of that happened not because of us or our failings, it happened despite us. So if we're going to do our part in improving decision-making on infrastructure, it's going to take a little bit of self-reflection. To be successful, you have to have an honest picture of your starting point. Who are we as a profession? What are our preferences? What do we like and what do we not like? So these are just a couple of views into, as a profession, the things we like to do. And one thing I'll call out is this whole idea, as Dr. Greg Becker says, we're Bayesian in our approach to our profession. And that just means we like to observe things and change our mind based on what we just observed. Or if you're a geologist, that means drinking and guessing. I'm a geologist wannabe. I'm an engineer. So, and then it's important to recognize the things we don't like to do, because those are often some of the obstacles in how we move forward. The other way to look at decision influence is to recognize there's really two major groups. So do we see ourselves as a provider of services, someone who queues up decisions for others to make? Are recommendations about our bottom line or our clients in a simplistic view? So we could look at ourselves in these two groups. Decision influencers, which primarily, that's probably most of the people on the call. Those are the folks that are technically oriented to their discipline or their project for which they're trying to provide solutions and answers often to difficult problems. Those solutions come from our education, our training, our experience, those elements of ourselves that make up our reputation. Really the key currency in our industry is our reputation. So we tend to be facts and evidence-based, and we tend to value precision. Decision makers, on the other hand, are often the clients, the owners, and they in turn need our help to justify the decisions they're trying to make. Often they must balance needs between competing priorities, projects, resources. Context is really important for them because they often must see the big picture in their decisions, and they are in fact part of a larger organization with other objectives. So they have this responsibility to the organization, to the society, and those that benefit from the projects. And the two are not mutually exclusive either. So that was the bit of self-reflection. So I really want to talk now about just the basics of influencing decisions so that we can all be on the same footing. So from my experience, there's really three things that make for a successful influence, and you'll see these as themes in the rest of my presentation. The target here is decision makers. In my world, that includes infrastructure owners, clients, regulators, policymakers, and investors. So decision makers are generally smart, experienced people that are used to making decisions. They have objectives and principles. We should know what those are. They have priorities. We should know what those are. Know how they've made decisions in the past and know what they're trying to achieve going forward. Essentially, we should seek to understand them first. The biggest mistake we make as influencers is trying to make them understand us first. So this is obviously two structural engineers talking about a problem. So the second thing is you have to recognize that in the first few minutes with a decision maker, you really have to make them interested enough to listen to your case. So don't try to explain what needs to be done. Don't try to explain how you do it. You're going to lose them. Convince them that they need to listen to you by explaining why. So why is the problem serious? Why it impacts them as a decision maker, why it relates to their corporate objectives, and why inaction can be really impactful to them. So more on why later. So if you get past the first two, you get to the real pitch, which is making the case for your recommendation, whatever it is. So we should be bringing evidence, facts, analysis, scenarios, case histories, making comparisons with other decisions and projects, explain the consequences and benefits of what you're suggesting, discuss alternatives considered but not chosen. So demonstrate some reasonableness. So in the state of the art decision-making guidelines today, you'll commonly see this referenced as making the case. So the last piece of background is just really on the decision process itself. So this should be familiar to everyone. If you look on the right, it's really how do we identify the problem, imagine solutions against that problem, compare and evaluate those alternatives, select and communicate the alternative, and then implement the decision. But there's common mistakes to avoid along the way. And then I've tried to list some of them on the left, and I'll talk more about these as we go along, but you can really group our mistakes into two larger groups. So it's mistakes that come from overconfidence. That's a premature understanding of the problem. That's starting out with the solution and finding problems that fit the solution. And it's really the rush to sub-optimize decisions because of external influences or false confidence in what we're pushing forward. The second real area is this whole idea of what is the state of decision practice, and I'll talk more about that. All right, so this list of influence techniques that don't work well is long, you know, and it's embedded in a lot of reports and letters and studies that few people read. That's one thing about decision makers, they don't read much. So I'm going to summarize for you, but to be clear, the problems we can identify as a profession are the problems we can solve. So that's why I'm focusing on what doesn't work first. So when the basis of your decision is compliance with a deterministic standard, and whose standards are based on limit state theory, so that's objects reaching equilibrium in physics, and where failures, risk analysis, case histories, experience, NORBAC analysis of failure supports these incidents as actual failures, you can have a credibility problem with decision makers. Limit states are fine as a starting point and a basis for design, but they make a bad basis for decision making by themselves. Infrastructure broadly doesn't meet standards because the environment in which it sits, including our policies, are dynamic. They change over time. An embankment designed and constructed 55 years ago That's a national average for dams and levees, has the standards of that day physically embedded in it. So trying to influence a decision maker based on a 1.3 factor safety for global stability may not pass the grin test. So what you see here is a project I'll talk more about later. And it's a levee system in the southwest US, and what you see there are shallow skin slides in the fat clay slope of the embankment. Now that was a $500 million project to repair that we didn't execute, and I'll tell you why. So this is really what following limit states has resulted in. The typical risk scatter chart. It's or an FN chart, if you will. I want to move something out of the way. So this shows 3,000 infrastructure systems in the US, and on the vertical axis you see the annual probability of failure, and on the horizontal axis it's consequences. So it's a log plot. So we use log plots when we have a data that spans an enormous scale. So this is all infrastructure that's been designed based on a set of standards. So 1 factor safety for exit gradient on seepage, 3 factors of safety on global stability. And what that results in is 7 orders of magnitude in difference in risk across the portfolio. So what does that mean? So there's a couple of findings you can pull out of this, this chart. One size doesn't fit all projects. Design should be informed by risk, and really compliance with the standards is important as a way to design things, but it hasn't really helped us understand projects or really manage risk. We've overinvested in some projects and underinvested in others. And so not everything's in our control. So let's talk about standards a little bit more. So, you know, like Dr. Becker said, we're all Bayesian, and so we like to use our experiences and the observational method to update our beliefs regarding infrastructure, how it should be designed and constructed, and we learn from our failures. So this is a little bit of a study done by Bryant Robbins and Scott Shoebridge in the Corps of Engineers, where they looked at about 200 years of the state of art in advancements in geotechnical design. And so they listed all these and they grouped them into these 7 different groupings you see here. And so what we see, looking at this, 65% of all major design advances in our profession occurred more than 50 years ago. So a strict discussion of the last 50 years really excludes most of what our profession has had to offer. In another way, you could say that if you read every geotechnical journal paper prior to 1970, you'd still be a current geo professional. So does any other profession have this orientation? Probably not healthcare or transportation or environment. Should these design standards be the basis by which we influence decision makers? So one thing I would say is just notice that most of the growth in the advancement of standards has come in the area of safety, risk, and seismic. Why is that? Well, the primary reason is that's where failures have occurred, and we've adapted our decision process to account for the failures. If you think of precision and accuracy as the 2 fundamental elements of decision making, then we have a choice as a profession. So again, what doesn't work well is choosing precision over accuracy. We should be choosing accuracy. And accuracy is really running the foot race in the right direction, and precision is running with good form and efficiency towards that direction. So we tend to associate precision, though, more with competency and consistency. But this is a critical mistake in the eyes of decision makers. And for me personally, I would agree with a quote from the famous economist that I'd rather be approximately right than precisely wrong. So why is our profession like that? Here's one of the reasons we have an inappropriate focus on precision, and that's as a profession, we believe decision makers demand precision. So we double down and we calculate another number to a greater significant digit for a limit state and express confidence in what we know. But we haven't changed what we don't know, the uncertainty. So this emphasis on precision builds a kind of false confidence. And so like the photo shows, it's analogous to standing on a thin sheet of ice over a deep frozen lake and dancing and celebrating what we know about the ice, but ignoring the 100 feet of frozen lake below it. So what else doesn't work? So telling instead of showing people is not a very effective influence technique. I had a friend of mine give me this update on the flooding in Houston, Texas during the Hurricane Harvey event of 2017. So it's precise and accurate. Meanwhile, we were wringing our hands because in the Gulf set Hurricane Nate. So we already had a probable maximum precipitation on the ground. And we're looking at something 50% greater than what anyone had designed for if Hurricane Nate came ashore. And the question became, was that possible? And if so, how are we going to communicate that to decision makers? So this is how the Houston Chronicle published information on that around the same time. So just as accurate and precise, that's a geometrically accurate volume of water that fell on Houston during Hurricane Harvey. But it's completely more informative to decision makers. It's because showing them rather than telling them is effective. Okay, staying with the theme of what's not effective to do is this not having a practical understanding of the problem we're trying to solve. So I wonder sometimes about the lack of practical experience in our profession. You know, we've moved beyond the stage of building new infrastructure. Now we're just rehabilitating old infrastructure. This is a bulldozer ripping an intact rock that has a compressive strength of 20,000 PSI. Also, we can replace it with 2,000 PSI concrete. So this should make us pause, right? A practical engineer might question why we're removing it instead of using it as the erosion resistant surface in the spillway. So inclusion of practical experience in how we influence decision makers is really important. One reason the FN chart, the risk plot I showed earlier, was an argument against using compliance with standard as the sole basis for decision making is this inherent incremental conservatism in our design and analysis process. So this incremental conservatism becomes a tyranny, and examples are the simplifications in models and programs regarding soil and rock behaviors, or conservative estimates of soil and rock properties rather than best estimates. Assumptions on drainage and pore water pressure that are conservative values for phi, C, and K, and you know, the fact that we're dealing with a natural environment that's generally non-linear, non-continuous, and non-uniform in the natural deposits. And then just the fact that our standards-based approaches are really looking at nodes within a larger failure. And that's a conservative approach. All right. So enough of that negativity. That's just a lot of that's just an example of mistakes I've made through the years. I want to talk about what I've seen to be really effective with decision makers. And so these are the good techniques. So remember the uncertainty paradox slide? Here it is from an alternate perspective. So what does work with decision makers in these really uncertain environments, decision environments? So we tend to focus on precision, collecting more data, carpet bombing sites with dozens of borings, and then express an overconfidence in what those mean and how effective they will be in influencing decisions. But what's really effective and actually effective is when we leverage basic science to more cost effectively fill those uncertainties and explain what lies beyond what we can see. So this has had two big outcomes in my view. on our profession. One is really unhealthy debate between geotechnical engineers and geologists regarding how to address uncertainty. I'm a fan of using science. And then the other thing that comes out of this is this idea of overconfidence and the bias that creates in decision influence. So if I asked you who had a greater overconfidence bias, engineers or scientists, what would you say? If I said the same thing for young or old professionals, what would you say? So what we know is younger folks and folks that come out of the science world have less overconfidence bias than older engineers. So what works really well also is decision makers appreciate influence and communication that recognizes their realities and objectives and are expressed with a healthy dose of fairness and reasonableness. So as this equation humorously seeks to illustrate, our profession can make it complicated, too complicated, and that sometimes causes us to miss the larger point of why we're doing something. So it's maybe converting our profession into thinking more about not meeting the standard, but what is the decision we're trying to support. So we spend years designing and building things by components, and Mother Nature doesn't really respect that. She works 24/7 to exploit those component interfaces that lack good integration, coordination, and systems view. The Challenger example illustrated this significantly. So as our profession gains a better understanding of how things can fail and their consequences, we're going to get a better understanding of what we should do about it. So the concept of potential failure mode analysis is probably the most central and significant advance that's led to better influence and better decisions. And it's really about problems we can understand better or problems we can solve better. So let me illustrate this a little bit further. So this is a real project example in our profession. I had a photo of it, the skin slides earlier in the presentation. So slope stability and our traditional focus on compliance with a factor safety approach. What does that really mean? So this is an actual example, and that's the results of an analysis. But if you had a factor safety of 1.0 for global stability, where there was 200,000 people below the infrastructure and several $1 billion in the economy, what would you do? How would you advise the decision maker in this case? Well, if you step back from that one calculation a little bit, from that limit equilibrium approach, you get to a little bit more of a more full understanding of what's really going on. And the stability analysis is really only the initiation node in a larger series of events. So you can understand that it's part of a larger set of events that have to happen. You can bring in the judgments of experts. You can evaluate it at multiple loading conditions. You can consider past performance at multiple loading conditions. You could be thinking about what happened before initiation and what follows initiation. Well, stepping back even further to understand the entire envelope of failure, we now see the original deterministic analysis as a single event highlighted in blue. So this larger understanding permits a few things to happen. So we get a better understanding of the problem and all the things that are influencing that initiation of a slope problem. We get an improved ideas about what the problem is and how to address the problem. So it's already informing us on what is the most cost-effective way to interrupt this stability problem. And then is an understanding of where the uncertainties exist and how or if they should be addressed. This is all evidence decision makers desire that bring more confidence to our decisions. So some say you should know your audience, but even better is to respect the audience. This captures the idea that you must seek to understand first the decision maker if you hope to influence them. So what decision makers expect from us is independent thought and critical thinking on the problems we face. Confidence in what we know and what we don't know. They expect us to honor this legal concept of the full truth, which is the truth, not lies. The truth, don't leave out other truths that are inconvenient, and nothing but the truth. So don't mix truth and lies. And so finally, they also want to see evidence that justifies the decision. And then finally, the thing that really works is reasonableness. That's really important. Decisions rarely have one clear winner. There's often gray areas that make decision options less distinct from each other. Decision makers know this from experience, and they like to see what was considered and the justifications for why those options were not forwarded. It demonstrates reasonableness and objectivity in the process, and it also may address that option that they personally believed was optimal, but was not. Okay, very quickly, just a few things that influence decision trends and challenges going forward. So not all decision makers are about better technical decisions. Sometimes they're going to be pulled in directions of money, time, or something else beyond the context of how we're trying to solve the problem. I think technologies like geophysical and remote sensing, which can have kind of a black box type of character, need evidence-based arguments to support their continued use in our industry. And then we live in this Bayesian world where we learn from our failures in our profession. But we need to be aware that decision makers may view this process of learning from failures a little bit differently than us. And then finally, a challenge is that how are we educating our young professionals? Are we within these silos that are necessary for their education, but the silos don't really reflect how the real world works? So looking into internal failure, in internal erosion failure modes really requires that you understand the frequency and episodic nature of hydraulic loadings, and you need to understand whether or not you're on the rising or falling limb of the hydrograph. And that's not something that's typically taught within the geo professions. So there's opportunities too. We're kind of data rich, but analysis poor, and we have opportunities now more than ever to have our analysis of data feed better decisions. I think the old decision metric of benefit cost ratio needs to be replaced permanently with risk-informed decision-making. I think we still need to show and not tell when we're trying to influence. And we need to professionalize our advocacy approach in a little more strategic way that like other professions are doing. So a couple of things on trends that are worth noting. Good decision practice incrementally improves, and that's happening with risk. So we're getting better at estimating extreme events, and we're building a stronger bench in industry to actually do risk analysis. We're grappling with the complexity that systems and human factors presents, but we shouldn't forsake or lose sight of the good governance practices we have that helps us manage that complexity. And then we're also part of this larger industry. And the industry has a number of decision trends which are evolving in its own way. So in the larger engineering and construction industry, social and behavioral science is now playing a larger role in decision making. So you see that in things like better analysis methods for loss of life. And risk is getting a more positive reputation as a way of taking the right risk on projects. Our world is hyper-connected, as we all know, and that's really amplifying the whole idea of reputational risk. And it makes me wonder what happens with the next failure. And then actually artificial intelligence. So we have all this data, and just like Uber married Google Maps with smart algorithms for a great product that a couple 100 million people use, there's some of that coming in our industry too, like INSAR, how INSAR is using AI to make dam assessments more effective. That's really promising. So kind of a final thought before we get into questions. This conundrum, why is risk embraced more in concept but not in geo practice? has led to a paper by I wrote with a colleague of mine. It's really about how we need to expose the resistance to change in our profession, and particularly as it relates to making better decisions. So sometimes we talk a better game than we practice, and that may leave us behind as decision influencers in comparison to other professions. So that's my last slide, and I think we're going to invite back in Greg and Pedro for Q&As.
So thank you very much, Eric. This was it's super interesting always to listen to you and what you have to say. I want to remind the participants, please, if you have, we have several questions that we have received so far, but if you have additional ones, please use the Q&A tab, and we will try to respond some of them. So a couple of questions, and we will do this together with Craig. So Craig Davis, anytime you can also please join the discussion. But one of the initial questions that we had is, would you provide an example of when compliance with geotechnical design standards resulted in an unconservative design or decision?
Yeah, so if you think back to that risk plot I had up, that had the 7 orders of magnitude in spread and risk across these infrastructure systems we designed essentially with the same set of standards. There's projects that just following the standards makes us conservative. So it makes us on the unsafe side of where we want to be. So an example there would be there's a big dam that's under rehabilitation in West Virginia now. It's called Bluestone. And so it had 2 competing problems that standards didn't do a very good job of helping us solve. So one problem was a sliding in the foundation of this gravity concrete dam. So it was a concrete rock foundation interface problem. Of course, we anchored it and made it stable. But that allowed, that was the risk driving failure mode. But at the same time, the hydrology and the hydraulic loads of the dam changed over time, and the dam now overtopped. So it was stable, but the volume of water that was now coming over the dam enabled scour to happen. And so the scour downstream of the dam attacked the very stability problem we were trying to solve in the first place. So the project went from about a $500 million rehabilitation to $1 billion rehabilitation to address this issue, that there had to be a redundancy and safety that standards weren't really picking up. So there's a lot of other examples like that as well.
Yeah, that shows you also for me, the complexity of the problems. Sometimes we identify some of the problems, but not all the possibilities. And of course, the immediate question that people are asking here is, what about on the other side of that plot, when you had used a design standard that resulted in a highly conservative decision? Any example where you said, I wish I had not put so much money on this?
So I think one of the design standards that has resulted in the most conservatism is how our profession chases the whole factor safety on exit gradient and seepage, right? So this is, we've chosen to characterize the whole failure mode on seepage as this one node that has to do with, does internal erosion initiate or not? And so that's caused us to go back and fix a lot of projects, put in a lot of cutoff walls, grout a lot of foundations, put in filters and stability berms. And probably the best example of that, where chasing that standard didn't really make any sense. It was overly conservative, and we could put an economical solution in place that actually works better, is Herbert Hoover Dike. So a lot of you probably have seen Lake Okeechobee in Florida. You can see it from a satellite map of the US. It's huge. It's got a 135-mile embankment that goes around it that contains it. Well, that whole embankment has historically had internal erosion and seepage problems. So when we went to look at it, if all we did was follow the standard on the exit gradient, we would have fixed all 135 miles. But the reality is, if you look at it from a decision standpoint, internal erosion needs several things. It needs not just for the internal initiation of particle movement on a downstream face. You have to have an unfiltered face. You have to have the ability to sustain a roof in the erosion pipe. And then you have to actually have an erodible material. So in most cases, that's a fine uniform silt or sand, which nature doesn't really put down in very long continuous layers. So when we looked at all of that, we ended up fixing a portion of that project. And I think we cost avoided $700 million by not just following the standard.
Interesting. So here I had, well, first of all, a comment somebody asked if you can provide the reference report paper for the levee system failure that you showed. If there is any reference, then you can send us that information. That was Amit Gakurel.
I can, and I will. It's published in the Journal of Risk Analysis, I believe, but I can send it to you.
So there's a question I wanted to feed off of your comment on complications, and it relates to decision makers and the community, and it came from the audience. But the decision makers, here's what it says, Eric. I'd like to hear your feedback on it. The decision makers are also increasingly members of the public, with the need to have consent to proceed with projects. How do we better support those folks in their understanding? And I think in my mind, that also leads to how the public and their perception of things, they'll try to influence the key decision makers, which in this case, I'm thinking like an elected official or something like that, instead of the engineer, regardless of what the engineer thinks. And so there's a complication, a very significant complication in there that goes well beyond calculations. And I would just like to hear your thoughts on that.
Yeah, that's a really good question, and it actually opens a whole can of worms. So I'll try to unpack it one worm at a time. Large projects like dams or levees or other projects that we'd call civil, they're called civil for a reason, because they're part of society, right? And so any project that happens like that, whether it's a new one or fixing an old one, does involve a contract with society. And that generally takes the form of some environmental documentation. So if you do a federal project, it's the NEPA process, the National Environmental Policy Act. That's where you actually engage the stakeholders in what you're doing, and they have a say in the things that make them happy and the things that make them upset. And that gets worked into the kind of decision you make. So there's a public stakeholder process that's out there for all projects. But I think the question has something else behind it, which is oftentimes as geoprofessionals, we're deciding what's best for the public, but it's kind of hidden within this concept of that's how we design things, right? So we're not asking the public how to do a calculation on a slope stability. We're deciding that, and we're actually deciding the safety margins on that, and thus the cost, and thus the impact on society. So the key thing is, when you're the owner, when you're the decision maker, you're making these decisions not from the public's perspective, but from your perspective on the trade-off between safety and economy. And so when you do things like risk analysis, and you say the risk is high, and then you use that risk analysis to make a decision on how to design something, you're not trying to interpret what the public thinks about the risk, because that's frankly unknowable. You're saying, as the owner, This is what I think about the risk. And this is how I consider the public's view of things like loss of life. And so there's actually a whole bit of science out there on this issue of tolerability of risk. And all industries, medical, transportation, legal, engineering, use this concept of tolerability. And it's really about, you can't know the public's tolerance for risk, but what you can say is, I choose to not increase that risk beyond which the most least at risk person faces. So that's the idea that, you know, a lot of our design standards are built around this 1 in 10,000 year event. And there's no accident to that. That is the fatality rate for a 13-year-old female in the United States, which is the lowest individual fatality rate in society. So if you don't increase it beyond that, then you're not increasing risk for people in general. That's how you get around the problem of not knowing what the public's individual tolerance for risk is. Because, Craig, some people bungee jump. I don't bungee jump. We have different tolerances.
You should.
So,
it's cool.
So I think that also begs the question that a lot of things that geoprofessionals do don't necessarily deal with life safety. So it becomes more complicated in not understanding the perspective of the community and what they want, especially if it's a high cost thing or very significant influence in the environment or their social well-being. But if it's not dealing directly with a life safety issue, like an embankment on a 5-lane highway, if that's not going to fail and slide into somebody's house, it might take out 1 lane for a little while it's being repaired, and maybe you just patch over it and you keep going for the next year until it rains again and causes it to move. Spending their money on that versus they might say, well, I'd rather have more low-income housing. And we don't know that as geoprofessionals, and that might not be the best example, but what I'm leading to is, how do we, and maybe it's just intended to be thought-provoking to everybody, but how do we ingrain ourselves to better understand those that we're actually intending to serve? And maybe that goes back to basic education and school.
So I do think that there's, in our education system and universities, in particular, we need to consider this idea of how our profession looks at risk, because risk is the great equalizers. It's what tells us when we're not integrated with other professions or disciplines, and really the thing you're getting at actually exists, and geoprofessionals are part of it. They just don't know it. And that is, when you have things like social equity, so it doesn't matter whether it's the parts per million in a contaminant and a treated wood, or whether it's the super elevation of a highway curve, or whether it's the stability of an embankment, there's this concept of don't impose an inordinate amount of risk on the person that's going to be interfacing with that engineering construction feature. So it's already there, and it is the social equity thing, and we don't see the trade-offs, but at the higher level, when people are trying to decide between low-income housing and a better road system, elected officials are having to do that. And so right now, elected officials are making those choices because they have a bunch of people squawking in their ear, right? The problem is, we're not squawking in their ear, it's others. Just because we're not comfortable or not good at the whole idea of how to influence decision makers. That's my view.
Yeah, but related to that, is when you have to say something or to hear something, the other side has to be also listening. And I have also a question about, do we have enough people on the decision maker side that are engineers, or how to do that? Because I don't see many engineers or civil engineers that are on that side. What have you seen? What is your experience with that?
I would say right now in my profession, if you looked at the people that are viewed as the top consultants in industry, right? The ones that are influencing big decisions. And the example I'd give you is John France, who led the forensic report on Oroville Dam. That guy, there's an incredible amount of trust in him because he's actually good at this whole job of understanding the big picture, debating, bringing arguments in a way that people can understand them and buy into them and support them. So I think if you looked at the top consultants in industry, they're attracting that attention and work and high pay because they're just good at that very thing.
There is one question that has repeated a couple of times, but one is Simon Wong from the USGS presented. And he says, thank you for a great talk. I must be missed it, but could you please repeat the key ideas for the slide on FM chart? That means the annual probability of failure scattergram. From this chart, what is currently not working and how can we do better?
Yeah, so that chart is the risk plot of 3,000 infrastructure systems in the US, right? And so on the vertical axis, you have the annualized probability of failure. On the horizontal axis, you have an annualized loss. It might be loss of life, it might be economic loss, but it's a log-log plot because as we designed these things over the last 100 years, they were designed with standards, and standards did not account for the fact that society is actually willing to invest more in things that are more important. In other words, you shouldn't design Oroville Dam like you do a 10-foot tall levee in a rural area of America, right? They should actually have different standards. So the big concept that comes out of that chart is standards are essential. They're the starting spot. They shouldn't be where we end up with design though, right? Design ought to be influenced by something other than just the standards. And that's the whole idea of risk-informed design is we're willing to invest more in areas where there's a greater likelihood or a greater consequence of something going wrong. So that the big takeaway there, and following standards, and really the whole idea of safety has been, if you comply with the standard, you're safe. That chart simply shows that that's not true.
Yeah.
Now, that's not the only piece of data that's changing in that chart, right? So over 100 years, you had science change, you had methods change, you had people developing land in and around dams and levees. There's a lot of other variables. But that was just to tease out the impact of standards on risk.
Yeah, good. So there are a couple of questions here that are go more to the education side of things. And we are getting close to the hour, but I want to ask at least this is, how do we assign risk to the different options or alternatives that we are considering in our design solutions? And the question here is from somebody that went to school in the 70s and the 80s, and risk was not really taught in big detail. And he claims that actually that has not changed so much in the last couple of years. But also, in another question, they also mention about a lot of these cases that because they are on litigation, they are never coming out, so they cannot be even explained. They cannot even be discussed. So what are your comments on that?
Well, starting with the last one first, I would say right now, if you go into litigation on design of a large dam or something like that, and you haven't used a risk-informed approach, you're going to be in trouble. Because right now, that's the state of the art. In the US, you have all 4 major federal agencies that are dam owners: the Corps, Bureau of Reclamation, TVA, and the Federal Energy Regulatory Commission. It's about 5,000 large dams in the US. They all have the exact same approach in how risk is embedded in their decision-making. Beyond that, you've got Canada. In Europe, you have Spain and France and the Netherlands and the UK. You just had India, the 3rd largest collection of dams in the world, go to a full risk-informed approach. And then Australians, New Zealand, big parts of South America are being developed by the World Bank with risk in mind, Africa as well. So I would say right now, that's the state of the practice. And if you're in a litigation issue, how do you not talk about it without seeming like you're on the outside of the state of the practice, when you're not up with the state of the practice? So I'm not sure I fully tracked the first question though.
So study more, study more. So Craig, any final question that you have for Eric before we close this?
Yeah, I do. I have one, and maybe it's simple. And this is a personal question that I observed as a manager and working with decision makers for much of my career. So you stated, are we one failure away from non-credibility? And my observation is that the geoprofessions were not given we are not given a lot of credibility on the onset when we're in the room with other technical professions. And so I would, and this comes from my observation, but I'm going to ask you this question. Are we too risk averse to gain credibility?
I just think the short answer is no. You know, I think the geoprofession is coming up faster now in risk than some of the other professions. Of course, the H&H folks are frequentists, so they were already comfortable with the ideas of probability distributions, right? This is what they deal with day in and day out. They took the risk like a duck to water. The structural folks are code compliance. So they're the ones that are actually most resistant to risk because they see their world as binary, safe or unsafe, based on whether or not you comply with the code. And their codes do have risk embedded in them, but it's not explicit. So the geoprofession is coming up quickly, and I think it's because they see it as answers to all the questions we've always had kind of growing up, right? How to deal with uncertainty, how to deal with problems like internal erosion, for which we still don't even understand the basic physical phenomenon of internal erosion, of how it happens. And so yet we're supposed to design around it. So folks are getting along with the idea of you could characterize some of these really complex things with failure mode analysis. So I think that our geoprofession will be fine. I would not take any discredit from the fact that we're uncomfortable. I think that's a good thing. What scares me is when the structural engineers are overly comfortable with code compliance.
Yeah. Understood. Thank you.
So I think, Eric, we are getting to the end of this webinar. We have several more questions here that we will pass them to you, and maybe there is an opportunity to answer them. I will just mention the last comment I got that said, fantastic presentation and discussion. Thank you. So I think that's a good end, and it talks about your ability to present this material. So I want to thank everybody for joining us today. I want to remind you that the webinar is going to be posted online, and information will be sent out when the recording is available. And again, the disclaimer that any opinions, conclusions, or recommendations expressed by anyone during this webinar are those of the individuals and do not represent conclusions or recommendations of the National Academies of Science, Engineering, and or Medicine. So with that, Eric, thank you very much again. And thank you everybody for joining us today in this webinar.
You're welcome. Thanks for the conversation.
Thank you very much.